Okay, so last time we took a look at how Newton's laws of motion apply to things that are moving in circles. Now we're going to start taking a different tack. With what we're doing here, everything going forward is basically, there's not going to be too much more that's truly new once we have momentum defined. Instead of absolutely everything we could ever want to do, we could do mechanics-wise with the physics that we've already learned. Now the thing is that in order to do that, you may have to do things like run computational simulations where you are attempting to model interactions molecule by molecule and stuff like that. Instead, what the physics community has found is that there are tricks you can use, certain truths that pop out from the physics that we've learned so far, Newton's laws of motion and the rules of kinematics, that allow us to study situations that you would think you could only do by computer simulation, but by exploiting those truths, we can simplify things greatly. So with that, let's go ahead and start by defining momentum. So symbol for momentum is a lowercase p. It is a vector and is defined to be the product of an object's mass with its velocity. And since mass is always positive, this means that the velocity vector and the momentum vector for something will always be parallel. Again, it's not meaningful to compare the lengths of the arrows you draw, because while the units of velocity are meters per second, here, since we're multiplying by mass, the units of momentum in SI units are kilogram meters per second. So since momentum and velocity have incompatible units, it doesn't make any sense to compare the lengths of the arrows. They're on a different scale. Now, the reason we care about this is as we go forward, we'll find that in collisions, if I add up all the momenta, so the plural of momentum is momenta. Momentum sounds like it's something used to help deal with really bad heartburn. But if we add up all the momenta of all the particles in a system before and after a collision, we'll show that that sum is the same both before and after. And a lot of times that'll give us a good enough answer for what we want without having to do full-blown computer simulations to get what we need. Now, just to put in as a side note here, just so I don't get anyone upset with me later, when you eventually get to learning about special relativity, you'll find that this definition of momentum will need to be modified. It'll have to be multiplied by a special factor to take relativistic effects into account. However, at the speeds we're going, anything that has ever been a part of your daily experience, this special factor to take relativity into account is a number just microscopically bigger than 1. And so we can go ahead and ignore it here. But just for full disclosure later, this definition will have to get modified a bit. So there are two factors that go into the momentum of a thing. So for instance, you could have, say, a small object here. Maybe it has a mass of 1/10 of a kilogram. Oops, 0.1 kilograms. And it's going at, well, let's say 100 meters per second. Its momentum would be pointed to the right. It would be equal to mv. So that would be 0.1 kilograms times 100 meters per second. And that would equal 10 kilogram meters per second. By the way, officially they say you should put a dot between units, but a lot of people get lazy and write dashes, so it's the same thing. We're not subtracting. But on the flip side, we could imagine, say, an object that has a mass of 1 metric ton. 1 metric ton is 1,000 kilograms. And we can say it's moving very slowly at, say, 0.01 meter per second, so 1 centimeter per second instead of 100 meters per second. Well, let's go ahead and figure out the momentum, shall we? P equals mv. So this would be 1,000 kilograms times 0.01 meters per second is still 10 kilogram meters per second. So to have a decent amount of momentum, you could be a lightweight object moving real fast, or you could be a heavy object and still have decent momentum moving quite slowly. So it's a combination of the two things. Okay, so this gets us back to the correct version of Newton's second law of motion. You'll remember when I put it up there before, Newton said the alteration of momentum is ever proportional to the motive force impressed and is made in the direction of the straight line in which that force is impressed. Now that we have defined momentum, we can go ahead and write this mathematically. So the correct version of Newton's second law says that the net force applied to a thing is equal to the time rate of change of its momentum. So it's probably worthwhile to see how we get the F net equals ma that we've been using. So let's make m equal to a constant. So in that case here, we can say, all right, this is the time rate of change of the momentum. Delta P would be, so this would be the change in the quantity m times v over t. But since the mass isn't changing, the change in m times v is the same thing as m times the change in v. And then you like say, oh my gosh, the change in v with respect to t is the acceleration. So if the mass is a constant, we recover the F net equals ma. If the mass is not a constant, then it's not as clean. And it turns out that you would have to resort to the methods of calculus to come up with other expressions, which is beyond the scope of our presentation here. So 99.44% of the time, you can get away saying F net equals ma, but if you have a system where the mass of a thing is changing, then we need to use this time rate of change of momentum thing. And it'll turn out that when you have collisions, sometimes you'll have collisions where you have fewer pieces flying out than you did coming in. Other times you'll have more pieces flying out than you did coming in. In both of those cases, clearly there was a change in the mass of the thing, of pieces of the system. And so we will develop tools to apply the correct version of Newton's second law for those situations. So to that end, let's go ahead and define the impulse. And basically what you're going to do is you're just going to go ahead and multiply both sides through by delta t, but we have to be careful. So, oops, let me write impulse here. So the impulse, which yes, we use the symbol capital J for, more on that in a second. It's a fun side note. If this is the force I'm applying on something as a function of time, let's say this is the x component of the force, we'll get that the x component of the impulse will be equal to the area under the curve in that graph. So we can write this as saying it's the sum of, over small time intervals, the force times the small time interval elapsed, or more correctly for us, we can say that the x component of the impulse of something would be equal to the area under the curve of, in a fx versus t graph, and the y component of momentum would be the area under the curve for a fy versus t graph. And yes, we could extend this to the z component as well. So our units of impulse are newtons times seconds. And if we play with that for just a moment, a newton times a second, remember a newton is a kilogram meter per second squared times seconds, gives me kilogram meters per second. And so the units of impulse are actually, have the same dimensions as the units of momentum. Usually we'll write impulse as newton seconds just so that we know that we're dealing with an impulse, and we'll write momentum as kilogram meters per second just so we can know that we're talking about a momentum. But this is maybe slightly less, it's a common thing, but it's not, it's a slightly less fussy thing than other times when we intentionally write units differently. Now, where this is really useful is for characterizing situations that I like to call hammer hits. In a hammer hit kind of a situation, you're dealing with a force that goes from 0 up to something huge, back down to 0, and you do that fairly rapidly. So for instance here, let's say you're designing, I don't know, a hammer. You might go and look and say, well, I want to make sure the hammer doesn't break, but I don't have a good idea of the maximum force the hammer might feel. But what you can do is you can come up with a reasonable definition of the average force by saying that the average force would be, let me change colors here. The average force would be the one that has the same area under the curve, so therefore the same impulse. So if we can find the value where the black and the pink areas are equal, we can go ahead and say that the constant force that does that for us is the average force. So let's say you're trying to design your hammer. You might be looking at the nail and saying, well, hey, the nail feels some sort, we can go ahead and say, okay, over about 20 milliseconds or so, let's say we feel a force that's maybe based on how the nail moves, we might say that the average force works out to be 500 newtons or something like that. And then when you're designing the hammer, what you might do is say, okay, we will design it to withstand a 5,000 Newton force, and hopefully that's adequately over-designed to take into account that my peak is bigger than the average. And we'll do a more thorough example of that in a second, but to do that example, I want to introduce the Impulse-Momentum Theorem. And what this comes from is if you take the corrective version of Newton's second law of motion, so F net equals delta P over delta T. Let's times it through by delta T. So we get delta P is equal to F net times delta T. If I now add this up over small time intervals, I will get that the change in momentum is, well, force times small time, and then I add it up over small time. The total change in momentum of an object will be equal to the impulse that it feels. So this is really just another way of writing Newton's second law, but it's a useful one. So for instance, to go back to our idea of analyzing forces, we might go and take a look at something like estimating how long the, how big a force might be. So to that end, we might go and take a look at our hammer and say, okay, when it drives, if I didn't have a piece of wood in the way and I just hit the nail, we might notice that the change in momentum of my nail was, let's say, 0.1 kilogram meter per second. You took some high-speed video to figure out how fast the nail was flying afterwards. You had figured out the mass of the nail. So from that, you can figure out the change in momentum of the nail. So we can go ahead and say, alrighty then, our change in momentum is equal to the impulse, and we had characterized that the impulse would also be equal to the average force times the time. So we can go ahead and say, all right, my average force that my hammer is exerting would be equal to, let's say, this 0.1, delta P over delta T. So that'd be my 0.1 kilogram meters per second. And I said 20 milliseconds, so 0.02 seconds. All right, so it's going to be 0.5, shift to 0. So about 5 newtons in this case. So for this particular nail, if I can design my hammerhead to say withstand 50 newtons of max force, then I feel pretty confident that I won't be in any danger of breaking the nail. Now, if I'm driving bigger nails or I'm hitting it harder or whatever, that would be different. That's just to give you some feel for how you can calculate an average force. So that's the one use that we have. And we'll get into the conservation momentum in the next video. But I just want you to take a look at what we've got here so far. And I want you to ask yourself why it is that cars are now required to have crumple zones. Crumple zones are, if you ever notice, if a car gets into a collision, often the front of the car is smashed up like an accordion. It did not always used to be that way. If you look at classic cars from the 70s and earlier, you'll find that if they get into a collision, they pretty much just barrel right on through with hardly a dent. So this is actually one of those cases where the crumple zones are not being put in order to sell more cars. there is a very specific safety reason for the requirement. And it has to do with the impulse-momentum theorem. So think about it for a second, and then we'll get back with you on it. Okay, so the idea is to literally buy you more time. Turns out with the old built-like-a-tank cars, you would go from, say, 60 miles an hour down to 0 in about 5 milliseconds. By having the crumple zone, you make the collision almost 100 times longer. The impulse is still the same because you're going from 60 to 0. The change in momentum is the same, therefore the impulse is the same. So that area under the curve is the same. But by making the collision last about 100 times longer, it reduces the average force by a factor of 100. And that is often the difference between a person being in an accident, then having to be buried, versus a person in an accident maybe having a couple broken bones or something like that. And that greatly enhances survivability in a crash. Okay, so in the next video, we'll take a look at the bigger application, or the more frequently used application of the impulse-momentum theorem, which will be the conservation of momentum. So I'll catch you in the next one.